So today I'd like to share with you our recent experiments on how we can move polaritons with external electric and magnetic fields. Before starting, I'd like to thank Thibaut Chervi, with whom I worked on this experiment, and also Martin Kroner and Atace Mamolu for their constant support. And also I want to highlight the collaboration with the group of Werner Wegscheider and especially the grower Stefan Feld for the samples we use in these experiments. So in a nutshell, what we did, we embedded our excitons in an electron gas, and by shaping density or spin density gradients in this electron gas, and then using electron-exciton interactions, we were able to transfer the response of electrons to the external fields to polaritons. So our work lies in this general context of equipping photons with new properties that they do not possess when traveling through ordinary dielectric media. And one unifying aspect, I would say, especially in the context of topological photonics, is that we have this requirement to engineer gauge fields for photons. And today we have many talks that are on very related topics, so I think I can just continue into the topics closer related. So now to external electric and magnetic field, I should mention the story starts kind of with an experiment by Daniele Sanvito and co-workers, where they showed that they can move bare trions with external electric fields. And also recently there was an experiment by the David Snow group on a type of drag on superfluid polaritons, but there also a recent clarification about the theory behind this work. And I want to highlight two proposals that are relevant to this topic of using external fields. So one is that we expect a finite Coulomb drag effect between electrons and excitons when they have a finite relative velocity. And more recently, by collaborators in our group, there's this proposal that in principle, polarons should be able to inherit any acceleration felt by electrons directly. So that are kind of, this is out. So however, what I'm going to share today with you is not really captured by those proposals, but still I will come back to those in the end, because I think it warrants further studies to find out what are then in the end the limits and possibilities of this fundamental question, how well we can control polaritons with electric and magnetic fields. So let me briefly introduce our system. We have a single gallium arsenide quantum well that is embedded in a DBR cavity, and the quantum well is doped with silicon in these thinner doping quantum wells, which are placed at nodes of the cavity field just to reduce optical absorption losses, but also to prevent this electric field from ionizing too many impurities and leading to unwanted changes in electron density. We then pattern this MBE-grown sample into a Hall bar shape and make electrical contacts to the 2-deck. And this kind of device then allows us to study the, let's say, interplay between electronic transport and polariton transport. And throughout the experiments, I will always use the same simple 2-terminal configuration. So I will quickly show it now. So we will always apply electric field from outside to either the left terminal or the right terminal, always along the long side of the Hall bar. And the other terminals are not needed. This sample is then cooled down to millikelvin temperatures for two reasons. First, it will allow us to access quantum Hall physics for the electron gas, but also generally narrows down all the optical features of the 2-deck. And then the rest is really standard. So below an optical window, we then have our optics, which allows the standard real space and Fourier space imaging experiments. So if we go towards the experiments, if we monitor the PL emission as a function of position, we see that the lower polariton energy traces out, first of all, the shape of our Hall bar, but then also has a slight variation along this axis, which is the cavity wedge. and checking then how the cavity mode crosses with the material resonances. Now that the exciton is embedded in this electron gas, we create collective trion-hole excitations that we may describe as attractive and repulsive polarons. So, and up here there is a feature from the light hole exciton, but we will mostly focus only on the heavy hole exciton polaritons. Now comes the main ingredient for our work. So if we now apply a bias voltage, which is outside of the linear response regime of this transport characteristic of our 2-deck, we create electron density gradient. So we're able to create an electron profile of basically controllable shape across the whole device. And then optically, we can verify this by scanning across the device and seeing that, let's say, on this right side where we apply the negative voltage, all the electrons are evacuated. And we have 3 polaritons corresponding to heavy hole, light hole, and cavity. And then as we move to the left to increase the density, we see that the heavy hole resonance will split into attractive and repulsive polarons. And then we see 4 lines. There should be a 5th because also the light hole is expected to split, but here in this condition it's not visible, especially because the polaritons overlap with the broad excitation spectrum of the 2-deck. So this is why we will mostly work with the lower polariton, which is always protected from overlapping with those resonances, thanks to the normal mode splitting. Then if we flip around the voltage, we will flip around the density gradient, and it's actually very smooth across the whole device, except there are these 2 bulges that you might notice, which happen to be due to strain. So they are exactly where the contacts are made. So they are also there in the absence of applying an electric field. We can visualize the same effect and see why this is useful to accelerate polaritons by looking in momentum space. So same setting once for the depleted device, we see 3 polaritons, and going to the electron, let's say, density case with maximal density, we see at least 4 resonances, and note that the change in asymptote energy here corresponds to the trion binding energy. And one, let's say, rough way to understand what will happen now is that the polaritons can lower their energy by seeking high electron density regions, because this polariton has a lower energy here than over on this side. So now we can spatially engineer those dispersions and use this to steer polaritons. How are we going to measure this? So if we excite resonantly with a laser, this will cut out the ring of the dispersion, which we will see as a dark ring in reflectivity. And if we look in cross-polarization, we will see the emission of the polaritons. We use cross-polarization because we don't have direct access to transmission in the current experiment. But it should be a good proxy. And then we see outwards propagating polaritons. And now what we do, we take such images, but comparing the 2 opposing density gradients. So one's gradient towards the left, one's towards the right, and compare these 2 images. And what we find is that there's a contrast. So how to read this? Let's say if the right side of the device is depleted, the polaritons want to move to the left, and vice versa. This is plotted in these difference images. So having this result, let me briefly explain one way to understand this with a very simple, basically classical model of polaritons as trajectories in an external potential landscape. So for this measure, we can independently measure the landscape exactly by measuring dispersions at different positions on the sample. And this then allows us to reconstruct the energy landscape and let's say launch a trajectory along the x direction of this image and get the green curve for how we would expect the polariton to move. And this overlaps pretty well with the experimental data. So this is the basic ingredient. So now allow me to introduce a magnetic field in Z direction. So what then happens, the electric field we apply always stays in the x direction. What happens is that the pattern starts to rotate. So now, as a function of the magnetic field and its sign, the polaritons get accelerated up to the transverse direction, even if for 40 millitesla. which saturates in this, the effect in this sense. And to understand what is happening, let's look at trajectory. So if, let's say we launch a polariton to the right, in this case where we have a density gradient corresponding to voltage on the right, which is this, corresponds to those red polaritons. So going to the right, this guy goes to the bottom of the device. Now, if we invert the picture, so in all these measurements, right, we have radially outwards propagating polaritons at all angles. So in particular, we have this one, which is also deflected to the bottom and goes down. So here you see that it's not a real Lorentz force, if you want, because inverting the velocity of our polariton doesn't invert the direction of deflection. And the way how we understand now what is happening is that as a function of magnetic field, we create a classical Hall voltage across the device, which is a new source of a density gradient which points transverse to the applied electric field. So far, so good. Then there's an interesting surprise that happens if we go to larger fields. So what is not surprising, of course, is that eventually the electrons will quantize into Landau levels. And the Zeeman spin subbands we can address with sigma plus and sigma minus polarized light. And then they have, of course, the famous transport signatures of the quantum Hall effect. In optics, it looks as follows for our sample. If we consider the filling factor 1, where just one Landau level is completely filled, we can efficiently make this transition with sigma plus to excite this exciton, and this is then dressed to a polaron with other electrons. On the other hand, the sigma minus is strongly suppressed because there's no phase space available. And if you put this in a cavity, this oscillator strength or density of final states translates into normal mode splitting. So the sigma minus branches come together, the sigma plus branches, they go apart. So now, if we position ourselves on the flank of such a plateau, we have an interesting new opportunity, because the sigma plus and minus branches slope in different directions. We will be able to have spin selective acceleration of polaritons. Let me show you how this goes. So in the experiment, now what we do, we again cut with a resonant laser, linear polarization, and now in the magnetic field, we will see two branches. Sigma plus branch is the outer one, the sigma minus branch, the inner one. And now if we apply our electric field, creating a gradient now in the y direction, due to the large magnetic field, you see that the two dispersion cones, I hope it's visible through the zoom lag, that they will shift against each other. So the two dispersions kind of are translated against each other. This shows that we accelerated two sigma branches against each other. It's instructive to look at this in real space. So here the experiment is a bit different. If we pump a particular point in K space and look at the right propagating polaritons, we see that if we again take such a difference image, that for one voltage, the sigma minus is deflected upwards, while the sigma plus is deflected downwards. And it flips again if you flip the direction now of the spin density gradient. And here it's also good to remark that the difference to some of the results we heard this morning. So here, the force on the polaritons or photons is not related to their K vector, but it is rather given by the externally imposed density gradient of electrons, or here, gradient of spin density. So with this, I think I want to already conclude my talk. So I showed you how we can accelerate polaritons in a tunable way using electron density gradients. And that's, if we manage to create spin density gradients, this leads to separation of sigma plus and sigma minus. And the effect we found here is distinct from Coulomb drag or a Lorentz force. And I think there's many interesting avenues to go from here. So I think we have this opposite regime of large current without density gradients that needs to be explored. And also very interestingly would be to follow this up using the Valley degree of freedom to get the spin density gradients in TMDs, and maybe follow up on the Valley Hall experiments, for example, by the group of Sven Höfling and Christian Schneider, to have a much easier handle on creating spin density gradients, which doesn't require quantum Hall or millikelvin temperatures. And very timely now, after the recent experiments on anion braiding, is again the question in fractional quantum Hall states, whether we will have any way to access optically that anions are in fact dressing our Polaritons. And with this, I want to end.
Thank you. Thank you very much for a beautiful talk. Please, question, please raise your hand and you're welcome. Yes, please.
It's me?
Yes, please, yes.
Okay. Thanks, Patrick. Very, very beautiful talk. I missed the you're applying a global shift to everything, correct? So when you say that you're moving everything, you're applying a global shift. And regarding your outlook, what do you think about how localized this drag could be? Or I don't know what you call it, drag or...
Yeah, so I think, I mean, we didn't design a sample particularly for this purpose yet. So I do think that by placing electrodes in a more let's say locally arranged, well-defined pattern, it would be interesting to create more complicated patterns of density profile. So I think this would be an option.
That you would turn them on and off and move something locally.
This also, yes, but also just to have, instead of two global contexts, more local contexts is, I think, perfectly possible.
Thank you. Somebody wants a question? Okay, so...
Just me, Barbara.
Oh, okay, because I don't see you. Hand. Okay, yes, please.
Thank you very much. Very interesting. Can you elaborate a little more on exactly what anions you mentioned, 5-half state? Is it 3-5 quantum well, or you have TMDCs here in mind, or whatever? I mean,
so here I have. Yeah. Sorry.
Yeah, exactly. And then you want to add on top because there is at least one paper, I think, right, by the group using very low temperature of Atach and colleagues using very low temperature and dressing it at least with a cavity already, but the effective temperature was not low enough to say. Is this a direction you want to pursue further, or?
Yes, I think after the recent success with electronic devices showing this anion interference, it's very much unrelated to my talk, of course. Mm-hmm. But it's related to the device. So I have in mind the 3-5 gallium arsenide sample where we have the fractional quantum Hall states already available. And here I think it would be interesting to think and try also an experiment harder whether we can get any handle on those anions. I mean, the anions are already there. The question is just how we make a smart enough experiment to show that, or to manipulate them, or to braid them. In an idea is, of course, the dream.
Mm-hmm. And how could strong coupling help here, compared to any cavity-enhanced first or recoupling first of all?
Yeah, so this is something we'll have to figure out. I also consider both options at the moment. I'm not completely sure if we gain by the Polaritons. I mean, we do have a more delocalized, let's say, spot, and knowing that the electronic excitations live on shorter length scales typically and have shorter coherence length, it might not be the most favorable idea to do it with the Polariton platform.
Mm-hmm. Thank you.
Thank you. Thank you so much.